Far beyond the reach of our everyday lives, hidden in the vast silence of space, lies a cosmos so incomprehensibly grand and mysterious that even our most advanced telescopes and theories can only begin to scratch its surface. And yet, it is in this very enigma that humanity finds its most profound questions that have echoed through the minds of ancient astronomers, brilliant physicists, and curious dreamers alike. For the universe is not merely a backdrop to our existence, but a living narrative of birth, transformation, destruction, and rebirth, written across time and space in the language of stars, gravity, and quantum threads. And when we look up at the night sky, we are not just witnessing distant lights scattered across a velvet canvas, but staring into the deep past, into epochs long gone, where galaxies collided, black holes devoured light, and the seeds of planets, and perhaps life, were planted in the fertile dust of supernovas. For every single photon that strikes our eyes after traveling billions of years carries with it a story, one of unimaginable energy, of unseeable forces shaping reality, of a universe expanding, cooling, evolving, and yet refusing to yield all its secrets. And as we delve deeper into the mysteries of dark matter, that invisible scaffolding that binds galaxies together, or dark energy, the force propelling the cosmos outward faster and faster, we are faced with truths that seem to contradict everything we thought we knew. For Newton's apple may have taught us about gravity, and Einstein's equations reshaped our understanding of time and space. But today's cosmos demands a new framework, one that stretches our intellect to its very limits. As we peer into the black holes that warp space-time so violently that not even light can escape, or decode the quantum fluctuations that might have birthed the universe itself from nothingness. And while some theories, like the multiverse, suggest our universe may be just one bubble among infinite others, each with different laws of physics, others propose that time itself may not be linear but an emergent property from a deeper reality still unknown to us. And as we build machines like the James Webb Space Telescope, capable of looking back to the dawn of galaxies, or fire up particle accelerators like the Large Hadron Collider in search of fundamental particles and hidden dimensions, we are not just chasing knowledge, but confronting the very boundaries of human perception and imagination. Because in these pursuits, we are not isolated observers, but part of the story, made from the same elements forged in dying stars, existing for a fleeting moment in a cosmos that will one day fade into darkness or collapse into a new beginning. And in that perspective, every equation, every experiment, every documentary, every spoken word becomes a spark, lighting a path through the unknown, a path driven not just by science, but by the sheer wonder of being alive in a universe that does not owe us answers, yet offers us glimpses of eternal questions if only we dare to look. And so the journey continues not just through the vacuum of space, but through the labyrinth of understanding, where each mystery unfolds into another, drawing us deeper into the fabric of reality. Where time dilates, stars are born from clouds of hydrogen, and gravity whispers across the emptiness, shaping the cosmic web. Because even though we may never fully grasp the totality of the universe in striving to understand it, we expand what it means to be human, to wonder, to seek, to know. In the earliest days of human civilization, long before the first telescope was ever pointed at the sky, ancient people looked up at the stars and saw not only light, but meaning. To them, the cosmos was divine and mythological, a dance of celestial deities whose movements foretold fate, guided the seasons, and offered glimpses into realms beyond mortal comprehension. From the ziggurats of Mesopotamia to the temples of the Maya, humanity's first understanding of the universe was rooted in observation, pattern recognition, and storytelling. The night sky became a canvas upon which early astronomers and priests charted the motion of stars, the recurrence of eclipses, and the wandering paths of planets, all without truly knowing what they were seeing. They built calendars, predicted solstices, and created some of the earliest records of celestial phenomena, such as the Venus tablets of Ammisaduqa or the Antikythera mechanism, long before the scientific method formalized our pursuit of cosmic knowledge. It wasn't until the ancient Greeks that a more systematic, mathematical approach to the heavens began to take shape. Thinkers like Pythagoras, who envisioned a cosmos of harmonic spheres, or Anaximander, who proposed that the Earth floated freely in space, planted seeds of inquiry that would grow over centuries. Most famously, Aristotle's geocentric model placed Earth at the center of the universe, surrounded by concentric spheres of stars and planets, a view later refined by Ptolemy and accepted for over 1,000 years. For a millennium, this Earth-centered model dominated Western thought, supported by both philosophy and theology, until it was challenged by a revolution that would shake the foundations of human understanding. The Copernican revolution of the 16th century marked one of the most pivotal moments in the history of science. Nicolaus Copernicus dared to suggest that Earth was not the center of the cosmos, but rather one of several planets orbiting the Sunday. This heliocentric model, initially controversial, gradually gained traction, thanks to the meticulous observations of Tycho Brahe and the mathematical insights of Johannes Kepler, who formulated his 3 laws of planetary motion, revealing that orbits were elliptical, not perfect circles as once believed. Then came Galileo Galilei, who turned his telescope toward the heavens and shattered the illusion of celestial perfection. He saw the craters of the moons of Jupiter, and the phases of Venus, all undeniable evidence that the universe was far more complex and dynamic than Aristotle or Ptolemy had envisioned. Galileo's discoveries, coupled with Isaac Newton's law of universal gravitation and laws of motion, offered a unified explanation of celestial and terrestrial motion, forging the classical mechanics that would dominate physics for the next 2 centuries. The Enlightenment pushed these ideas further, turning astronomy into a quantitative science and encouraging exploration beyond our own solar system. The 20th century brought a second scientific revolution, this time in our understanding of space, time, and the very fabric of the universe. Albert Einstein's theory of general relativity in 1915 redefined gravity, not as a force, but as a curvature of space-time itself, allowing for the possibility of black holes, gravitational waves, and an expanding universe. Around the same time, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to discover that the Andromeda Nebula was, in fact, a separate galaxy beyond the Milky Way, fundamentally altering our concept of the universe's size. Hubble went further, observing that galaxies appeared to be moving away from us in all directions, leading to the realization that the universe is expanding, a discovery that became the cornerstone of the Big Bang Theory. This model posits that the universe began as an unimaginably hot, dense singularity, approximately 13.8 billion years ago, and has been expanding and cooling ever since. Supporting evidence soon followed, including the discovery of cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965, which provided a faint echo of the universe's fiery birth. Throughout the latter half of the 20th century and into the 21st, a series of groundbreaking milestones in cosmology and space exploration have further refined our understanding of the cosmos. The launch of space telescopes such as Hubble in 1990 opened a new window into the universe, allowing astronomers to observe distant galaxies, dying stars, and nebula with unprecedented clarity. Missions like Voyager 1 and 2, launched in 1977, journeyed past the outer planets and continue to send data from interstellar space. The discovery of exoplanets, planets orbiting other stars, exploded in the 1990s and 2000s, with thousands confirmed to date, suggesting that planetary systems may be the rule, not the exception. The detection of dark matter and dark energy added new layers of mystery. Together, these unseen components are believed to make up over 95% of the universe's total mass-energy content, yet they elude direct detection. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, announced the first observation of gravitational waves, ripples in space-time caused by massive cosmic events like merging black holes, confirming another of Einstein's century-old predictions. These discoveries have revolutionized not just our knowledge of space, but also our understanding of the universe's structure, origin, and ultimate fate. One of the most profound ideas to emerge from modern cosmology is the concept of the observable universe. Given that the universe has a finite age around 13.8 billion years and that the speed of light is constant, there is a limit to how far we can see in any direction. The observable universe is essentially a sphere centered around Earth, with a radius of about 46.5 billion light-years. Due to the ongoing expansion of space, it is not a boundary of existence, but a limit of perception. Beyond it, more galaxies and cosmic structures likely exist, but their light has not yet had time to reach us. This observable limit challenges our sense of scale and forces us to confront the possibility that the universe is not only vast, but potentially infinite. It also raises philosophical and scientific questions about what lies beyond. Could the laws of physics change? Could other pocket universes exist as part of a broader multiverse? Our tools and theories continue to evolve as we attempt to probe these mysteries. But for now, the observable universe remains our cosmic horizon, a glowing echo of the past, constantly expanding and revealing the universe's story as we refine our questions and instrument. Today, as we stand on the edge of another era in space exploration, with new telescopes like the James Webb peering deeper into cosmic history than ever before, private space companies pushing boundaries once reserved for government agencies, and missions planned to Mars, Europa, and beyond, we carry with us the legacy of thousands of years of curiosity, calculation, and courage. From the mythological heavens of ancient civilizations to the particle fields of quantum cosmology, our understanding of the universe has undergone revolutions that not only changed what we know, but redefined what we are capable of imagining. Each discovery is both an answer and a provocation, revealing new layers of complexity and wonder, reminding us that while we have come far, the journey into the cosmos has only just begun, and the true shape of the universe, its origins, its structure, its fate, continues to unfold before us like a story still being written in the stars. There's something indescribably profound about looking up into the night sky and realizing that the tiny pinpricks of light shining through the darkness are not just stars, but ancient beacons, some long dead still, casting their light across time and space. And when we take a moment to truly reflect on that, to let it sink in, we come face to face with one of the greatest emotional paradoxes we can experience as human beings: the overwhelming smallness of our existence, juxtaposed with the sheer miracle that we are here at all, capable of witnessing it, of questioning it, of yearning to understand our place in something so vast and unknowable. It is in this moment, standing beneath the stars or watching a distant galaxy swirl on a screen, that a quiet sense of awe takes hold, a feeling that transcends science and touches something ancient, spiritual, even poetic within us. For the universe is not just a place, it's the ultimate mirror, reflecting back our fears, our hopes, our questions, and our deepest emotions. Why should people care about the cosmos? Because the story of the universe is, in a very real way, the story of of everything we've ever known, everything we will become, and everything we might never understand. And in a world that often feels chaotic, painful, and divided, the universe offers a rare glimpse of unity, of scale, of shared origin. For every human being on Earth, no matter where they are born, no matter what they believe, is made of the same stardust, forged in the same violent supernovae, woven from the same cosmic fabric that stretches across billions of light years. There is something deeply comforting in that, an emotional anchor in an otherwise uncertain existence. For if we are all part of the universe, then perhaps we are not so alone, and perhaps there is meaning to be found in the search itself. But caring about the universe is not just about comfort, it's also about facing the raw, unsettling truth of the unknown. There is a particular type of fear that comes not from horror or danger, but from scale, from staring into the infinite and realizing there are no edges, no walls, no boundaries to protect us from the questions we can barely form, let alone answer. What lies beyond the observable universe? What existed before time began? Are we alone? Or are there other minds out there also searching, also wondering, also afraid? These are not just scientific inquiries. They are emotional riddles that confront us with our fragility, our impermanence, our desperate need for connection and purpose in a cosmos that remains silent. And yet that silence is not empty. It's filled with potential, with mystery, with the invitation to explore not only what lies out there, but what stirs within us when we dare to look. The cosmic void, with all its terrifying indifference, also holds a kind of brutal beauty, because in the face of its coldness, we burn brighter, not just as biological entities, but as conscious beings who dream, who imagine, who build rockets and telescopes and theories to chase whispers of the beginning. There is courage in that pursuit, in the willingness to confront the unknown, not with resignation but with wonder, with a childlike curiosity that never truly leaves us, no matter how old we get or how sophisticated our instruments become. That emotional resonance runs deep. It's the spark that leads a child to ask, "Where did we come from?" or stare wide-eyed at Saturn's rings through a telescope. It's the quiet gasp you hear in a planetarium when the screen zooms out from Earth to reveal the scale of the Milky Way. And then again, when the Milky Way becomes just one point among billions. It's the heartbreak of realizing how rare and delicate life is, the existential weight of knowing our sun will one day die, the awe of watching a rocket disappear into the sky while holding your breath. It's the late-night conversations about aliens, parallel universes, or what happens after death, not because we know the answers, but because the very act of wondering connects us to something bigger. The universe forces us to ask the questions that matter. Who are we? Why are we here? What is consciousness? What does it mean to be alive in a universe that may never reveal all its secrets? These questions have no easy answers, and that's precisely why they matter, because in grappling with them, we become more human, more honest, more humble. Moreover, the emotional engagement with the cosmos has always been a driving force behind progress, behind creativity, behind the things that move us forward as a species. It's not just about building telescopes or sending rovers to Mars, it's about art inspired by starlight, music echoing the rhythm of planets, literature reaching for metaphors to capture the infinite. The universe has always been our muse, pushing us to dream beyond the boundaries of Earth, to paint with colors unseen, to compose symphonies that echo the vastness of space, to write stories that span galaxies. And in today's world, where we often feel disconnected from each other, from nature, from meaning, the universe offers a chance to reconnect not just with the cosmos, but with ourselves, with that primal part of us that still remembers the firelight and the stars above, that still feels the pull of distant worlds and cosmic time. It reminds us that even in our darkest moments, we are part of a much larger story, one that began long before us and will continue long after, but which we, for a brief and beautiful moment, get to be part of. And yet, the emotional power of the universe is not limited to the grand and the vast. It is also found in the deeply personal. For someone standing on the edge of a crisis, staring up at the stars can offer perspective, a moment of clarity, a reminder that their pain, while real, exists within a much broader canvas. For someone who feels lost, the cosmos offers a direction, not in the literal sense, but in the way that questions can guide us toward purpose. There are countless stories of people finding solace in the night sky, of scientists who became astronomers because they lost a parent and wanted to feel closer to them, of writers who looked to the stars during times of war and wrote poems that spoke of peace. The universe is not just out there, it's in us, in our emotions, in our struggles, in our triumphs, and perhaps most beautifully, it is not finished. It is still evolving, still expanding, still creating, and so are we. That parallel, that shared journey between cosmos and consciousness, is one of the most profound emotional truths we can embrace. So why should people care about the universe? Because it reminds us of who we are and who we might become. Because it challenges us to grow, to explore, to feel, to question. Because it holds our history in its atoms and our future in its stars. Because in its silence, we find our voice, and in its darkness, we find the courage to shine. Because in the vast unknown, we discover the depth of our own hearts. Caring about the universe is not a luxury, it is a necessity for anyone who wants to understand not just what is out there, but what is within. In an age of distraction and division, it is the one thing that can still unite us, still humble us, still fill us with wonder and the desire to beyond. And ultimately, in the search for distant galaxies, black holes, and alien worlds, we are really searching for ourselves, for meaning, for connection, for the story of how something so small could dare to imagine the infinite. If you've ever stared into the night sky and felt something stir deep within you, a quiet sense of longing, a rush of questions you couldn't quite form, or a sudden awareness of how strange it is that we exist at all, then you've already taken the first step into the mystery that surrounds us. But what if those questions aren't just idle thoughts? What if they hold the power to change the way we see everything? What if, buried in the stars, in the cosmic background radiation, in the quantum dance of particles, lies a secret that could upend our understanding of reality itself? Consider for a moment, what if we're wrong about how time works? What if space isn't a void, but a field alive with hidden energy? What if consciousness itself is somehow connected to the fabric of the universe? These are not science fiction fantasies. They are real questions being explored by physicists, cosmologists, and philosophers around the world. And they are questions that you, the viewer, can engage with not as a passive observer, but as a curious mind capable of diving deeper. Why does the universe appear so perfectly tuned for life? Why can we describe its behavior so precisely with mathematics? Is that just coincidence, or does it mean something more? These mysteries aren't just puzzles for scientists. They're invitations for all of us to look at reality, not as something fixed and known, but as something alive, changing, and filled with potential we've barely begun to grasp. Take the idea of parallel universe, a concept once confined to speculative fiction, but now taken seriously by many physicists. If our universe is just one of many, if infinite versions of reality are unfolding simultaneously in dimensions beyond our perception, what does that say about choice, destiny, or free will? Does another version of you exist in a universe where you made a different decision? Does that mean every possibility is real somewhere? Suddenly, the choices we make, the paths we take, begin to feel both more significant and more mysterious. Or consider the implications of discovering intelligent life beyond Earth. For decades, we've scanned the skies with radio telescopes, listening for signals from distant civilizations. If tomorrow a message came through a real, confirmed signal from another world, how would it change your view of life, religion, meaning, or humanity's place in the universe? Would you feel excited, terrified, inspired, insignificant, or deeply connected? The truth is, we don't know how we'd react, but we do know this: it would change everything. And yet, that possibility isn't distant, or theoretical. It could happen within our lifetimes. The next breakthrough might come not from a lab, but from a conversation, a new way of thinking, or a question asked by someone who never thought of themselves as a scientist at all. Why does any of this matter? Because the mystery of the universe is not separate from our daily lives. It's woven into them, into the way we perceive time, identity, purpose, and connection. Understanding the cosmos isn't just about stars and galaxies. It's about understanding how we fit into a larger story. It's about expanding our awareness beyond the routines of life and realizing that we are part of something ancient, ongoing, imaginably vast. That realization can reshape how we treat one another, how we care for our planet, how we value knowledge, creativity, and curiosity. Every new discovery, from the bending of space-time to the detection of gravitational waves, adds another thread to the tapestry. And every time we stop to reflect, to ask why, we participate in the creation of a more conscious world. The potential impact of these discoveries is enormous, not just technologically or scientifically, but emotionally, ethically, and philosophically. What if understanding the Big Bang helps us create better models of how systems evolve from economies to ecosystems? What if quantum entanglement teaches us something profound about connection, about how actions ripple outward in ways we can't see? What if the pursuit of understanding teaches us to be more humble, more united, and more awake to the miracle of existence? This is why your participation matters, not just as a viewer, but as a thinker, a dreamer, and a question asker. You don't need a PhD to wonder why the speed of light is constant, or to ponder the paradoxes of infinity. You just need curiosity and a willingness to lean into the unknown. So ask yourself, what do you believe about reality? Where do you think the universe came from? What do you think consciousness is? Could time exist without memory? Could space exist without observers? What if the deepest truths are not found in textbooks, but in the questions we're afraid to ask? What if our greatest discoveries lie not in answers, but in the willingness to explore the mysteries that make us feel small. Because it's in those moments when we feel humbled, awestruck, uncertain that we grow. And when we share those questions with others, when we debate, discuss, challenge, and collaborate, we begin to move as a species, not just as individuals. Think about the next generation children born today who might one day walk on Mars, who may grow up with telescopes powerful enough to see the first stars ignite after the Big Bang. What kind of questions will they ask? What kind of world will we leave them if we fail to nurture curiosity? If we tell them that space is too abstract, too far away, too unimportant? What kind of breakthroughs might we miss if we stop believing in wonder? This is not a time for apathy. It is a time for engagement, for reflection, for sharing ideas and challenging assumptions. We live in an age where the boundary between the known and the unknown is shifting faster than ever before. Artificial intelligence is accelerating scientific discovery. Space tourism is becoming reality. Quantum computing is redefining what's possible. And yet, the biggest breakthroughs may still come from a simple question asked at the right moment. What if you're the one to ask it? What if someone you inspire goes on to unlock a mystery that changes everything? So let this be an invitation, a call to curiosity. Don't just watch the stars. Ask why they shine. Don't just accept what you've been told about space, or time, or existence. Explore it. Talk about it. Debate it. Dive into the wild theories and mind-bending paradoxes, not because you need to solve them, but because wrestling with the unknown is what makes us human. The universe doesn't owe us meaning, but it gives us the opportunity to create it. Each time we dare to look deeper, to wonder harder, we participate in something far greater than ourselves, a legacy of explorers, thinkers, poets, and rebels who refused to accept the world as it is and reached instead for the stars. What will your role be in this cosmic story? Will you let the mystery pass you by, or will you step into it, eyes wide open, ready to ask the next big question? Because one thing is certain, the universe is listening not with ears, but with infinite potential, and your curiosity might just be the spark that illuminates the next great chapter of discovery. Imagine drifting through the void, not as a body bound by Earth, but as a consciousness free to roam, unanchored and aware, moving silently across a stage woven in darkness and light, where time no longer feels linear and space becomes a living ocean of possibility. The temperature drops to near absolute zero, where molecules barely move, and yet, beyond comprehension, entire galaxies swirl like whirlpools of light, tens of thousands of light years across, each holding hundreds of billions of stars, each star potentially orbited by planets, some of them lifeless deserts, others perhaps teeming with forms we cannot yet imagine. There is no up or down here, only directionless immersion in the greatest silence ever known, an endless black sea pierced by ancient fire, where light takes millions or billions of years to reach the edge of our awareness. These stars, these glowing crucibles of hydrogen and helium, are born in dense clouds of cosmic dust, live furious lives of nuclear fusion, and die in spectacular explosions, supernova scattering heavier elements into space, birthing nebulae, seeding planets, forming the raw ingredients for life. In the vast spaces between them lie regions so empty they defy language, galactic voids, where gravity's pull cannot reach and light rarely ventures. And yet, even here, even in emptiness, something holds the universe together. An invisible web of power known as dark matter, mysterious, unseen, detectable only by its gravitational effects, shaping the cosmic structure, like the bones beneath the skin of the universe. In one direction, you pass through the arms of a spiral galaxy, blue with hot young stars and pink with glowing hydrogen gas where new suns are being born. In another, you skirt the edges of a massive elliptical galaxy, golden and aged, its stars older than Earth itself, burning steadily like the embers of a fire that began before time as we know it. Then you drift beyond even these into the massive filaments of the cosmic web structures, so immense that they stretch across hundreds of millions of light years, connecting clusters of galaxies with strands of invisible matter, while the voids between them grow even darker and colder. This is the large-scale structure of the universe, not random, not chaotic, but astonishingly intricate, almost organic in its scale and elegance. And the more we see, the more questions arise. Why does the universe have this shape? What force pushed it into such patterns? What lies beyond the edge of the visible, where light from the most ancient sources has not yet had time to reach us? Amid these questions, we find the key players, human minds, who dared to look into this darkness and try to make sense of it. There was Albert Einstein, whose equations of general relativity cracked open the possibility of a dynamic universe, where space and time are not fixed but malleable, curved by mass and energy. There was Edwin Hubble, who first measured the redshift of galaxies and revealed that the universe is expanding, thus igniting the flame that would become the Big Bang Theory. Georges Lemaitre, the Belgian priest and physicist, who first proposed that the universe originated from a primeval atom, introduced a spiritual elegance to the scientific tale. Later came Vera Rubin, whose observations of the rotational curves of galaxies provided the first compelling evidence for dark matter, a discovery long overlooked by the scientific establishment but now recognized as one of the pillars of modern cosmology. Today, the torch is carried by scientists like Brian Greene, who explores the far frontiers of string theory and the multiverse; Sean Carroll, who challenges conventional views of time, entropy, and cosmological origins; and Katie Mack, who speaks not just of the universe's beginning, but its potential ending sheet death. Big Rip, Big Crunch, with both precision and poetic reverence. These thinkers, and many others, exist as points of light in the intellectual cosmos, mapping out the edge of the known and peering beyond it. And as their instruments grow more powerful, from the Hubble Space Telescope to the James Webb, from LIGO's gravitational wave detectors to the Event Horizon Telescope that imaged a black hole shadow for the first time, we are beginning to see space not just as distant and exotic, but as intimately connected to the ground beneath our feet. Because we are part of this cosmos, our atoms come from stars, our time flows with cosmic time, and our questions, our theories, our explorations, they shape how we experience the universe. Just as the universe shapes us, each new discovery adds to the atmospheric richness of this cosmic setting. Like discovering that the majority of the universe is made of dark energy, a force not only expanding the cosmos, but accelerating its expansion in a way we cannot yet explain. Or that space is not flat, but slightly curved, implying geometry on the scale of the cosmos. Or that the early universe underwent a period of rapid inflation, a moment of growth so fast and so violent that it dwarfs any known process, giving birth to the very structure we now observe. And yet, despite these revelations, the atmosphere of the universe remains one of awe, of breathtaking mystery. It is in the silent drama of a neutron star colliding with another, sending ripples of space-time across the galaxy. It is in the quiet glow of a distant quasar, a black hole consuming matter at such a rate that it outshines entire galaxies. It is in the haunting symmetry of Einstein rings, where the light from a distant galaxy is bent around another by the warping of space itself, creating a perfect circle in the sky. Each of these phenomena is both terrifying and beautiful, beyond comprehension, and yet increasingly within the reach of our instruments, our mathematics, and our storytelling. To be immersed in this setting is to feel small, yes, but also powerful, to know that while we cannot reach the edge of the universe, we can model it, simulate it, ask questions of it, and draw meaning from its behavior. And what tone could better suit this journey than one of humility mixed with ambition, fear tempered by curiosity, mystery woven through with data? Because to build atmosphere in this cosmic context is to understand that atmosphere itself, on Earth or in the mind, is born from contrast, from light and dark, from silence and signal, from the interplay of knowledge and wonder. It is in the dissonance between what we know and what we do not, between our desire to master the universe and our need to be mastered by it. The cosmos is not just out there, it is a place of metaphor, of emotional resonance, a setting in which our greatest fears and highest hopes can unfold. And in this atmosphere, science is not cold or mechanical. It is an instrument of poetry, of exploration, of truth-seeking that does not demand answers, but invites engagement. The more we know, the more beautiful the unknown becomes. The deeper we look, the more we realize how much lies hidden. And yet we continue, driven not by certainty, but by the atmosphere itself, by the gravitational pull of curiosity, the radiation of awe, and the quiet hum of the human spirit seeking its place among the stars. So let yourself drift here a little longer. Let your imagination move across the rings of Saturn, through the frozen oceans of Europa, down the gravity well of a black hole where time dilates and space stretches. Let yourself wonder what the surface of an exoplanet orbiting a red dwarf might feel like beneath your feet. Let yourself imagine standing at the edge of the observable universe, watching the last photons reach you from a galaxy now gone. Because this is not just set in his story, this is not just space at his stage. And you, as a conscious being aware of all this, are a participant, an explorer, a co-author of the greatest narrative ever told, the story of the universe discovering itself. As we reach ever farther into the cosmos, building bigger telescopes, running deeper simulations, and formulating more daring theories, a quiet tension builds beneath our progressive sense that despite all we've achieved, there may be barriers we can never cross, limits embedded not just in our tools or methods, but in the very fabric of reality itself. From the earliest days of cosmology, subtle clues have hinted at this coming conflict, a looming truth that we may be chasing questions with no final answers, peering into a universe that might never allow us to fully see its edges, let alone understand them. The observable universe, defined by the speed of light and the age of the cosmos, forms a kind of cosmic bubble around us, not because nothing lies beyond, but because light from those regions hasn't yet had time to reach us. That limit, approximately 46.5 billion light-years in every direction, is not a physical boundary, but a wall of information, an epistemological horizon that grows only as the universe ages, and even then, only reluctantly. What lies beyond it may remain forever hidden. This fundamental limitation, born of the very laws that govern our reality, is not just a technical challenge, it is a philosophical one, for it means we may never be able to speak with certainty about the totality of the universe, only the portion we can see, and even that is filtered through the distortion of cosmic expansion, gravitational lensing, and ancient light stretched thin across the ages. Early in the 20th century, the tension began to show. Einstein's equations of general relativity were elegant, powerful, and predictive, but they also hinted at strange and troubling possibilities: black holes, where time stands still, wormholes that could connect distant regions of space, and singularities where physics itself breaks down. The very structure of space-time, once thought to be a smooth backdrop, was now dynamic, bendable, and potentially chaotic. Meanwhile, quantum mechanics emerged with its own set of paradoxes: particles that exist in multiple states at once, uncertainty built into the heart of measurement, and entanglement that defied locality. The two great theories of the 20th century, relativity and quantum mechanics, each revolutionized our understanding of nature. Yet they remain stubbornly incompatible, suggesting that a deeper, unified framework still eludes us. This unresolved tension has haunted physics for decades, and every attempt to reconcile them, whether through string theory, loop quantum gravity, or other quantum gravity candidates, raised as many questions as answers. These paradoxes are not just mathematical quirks. They are signals of a deeper conflict, a message written into the equations. We are missing something fundamental. Adding to the challenge are the observational constraints that arise from our very place in the cosmos. We are limited to a single vantage point, located on a small planet in a minor galaxy, and our observations are always filtered through local conditions, instrumental noise, and cosmic interference. The further we look, the older the light we see, meaning that distant galaxies are not just far away, they are also young, distorted by expansion, and often hidden behind clouds of dust or washed out by background radiation. And yet, we try. We listen for neutrinos and gravitational waves. We analyze the polarization of cosmic microwave background radiation. We model the evolution of structure across billions of years. But the deeper we go, the more we realize how dependent we are on inference, not direct observation. We cannot see dark matter, only its gravitational fingerprints. We cannot isolate dark energy, only detect its effects in the acceleration of cosmic expansion. Even the Big Bang, the foundational event of modern cosmology, is not something we can observe directly, its aftermath, scattered across the sky in ancient photons, like the fading smoke of a fire long extinguished. This is where the conflict sharpens. For all our knowledge, for all our breakthroughs, we may be trapped within a cosmic shadow play, seeing only the flickering silhouettes of deeper truths we cannot touch. Some physicists now suggest that the very idea of an edge to the universe might be a flawed question, that the universe, infinite or not, may have no boundary in the way we imagine, but rather folds in on itself or extends indefinitely in dimensions we cannot perceive. Others argue that our reality may be a hologram, a projection from a more fundamental layer of physics operating beyond space and time. And yet others suggest that we might live in a multiverse, where our universe is just one of countless others, each with its own laws of physics, unreachable by any signal, untestable by any experiment. These ideas, while fascinating, carry with them a heavy implication that some aspects of reality may forever lie beyond the reach of science, not because we aren't clever enough, but because the structure of reality does not allow it. This challenges the very heart of scientific inquiry, which is built on the belief that with the right questions, tools, and time, any mystery can be solved. What if that's no longer true? Throughout history, our understanding has constantly been challenged, often in the moments we thought we knew the most. The geocentric model collapsed under the weight of better observations. Newtonian mechanics gave way to relativity. Deterministic physics crumbled before the probabilistic haze of the quantum world. Each time, we were forced not just to revise our theories, but to rewrite our assumptions about space, time, matter, and ourselves. Today, we stand at a similar threshold. The acceleration of the universe's expansion suggests that most of what exists is invisible and untouchable. The behavior of particles at the quantum level suggests that reality is not fixed, but probabilistic and context-dependent. The discovery of non-local phenomena, like quantum entanglement, challenges our most basic intuitions about cause and effect. And the inability to unify gravity with quantum theory casts doubt on the completeness of our most cherished models. These are not failures, they are signs of progress, but they also suggest that our journey toward truth is far from over and may never be complete. And yet, paradoxically, it is this very conflict, the tension between what we know and what we may never know, that gives science its power. It is in the questioning, the reaching, the struggle to reconcile conflicting evidence that the spirit of discovery is most alive. When we build observatories to detect gravitational waves, we are not merely confirming predictions, we are reaching into the darkness for new clues. When we simulate the early universe on supercomputers, we are not just playing with numbers, we are invoking the birth of time and structure. Every paradox is a promise, every limitation an invitation. The mystery of the cosmic edge, the impossibility of perfect knowledge, the dream of a final theory, all of these fuel the engine of inquiry, challenging us to imagine more, to think deeper, to remain humble in the face of the vast and the unknown. So while the signs are clear that we may never reach the ultimate answers, never fully grasp the true shape of the universe, never resolve all paradoxes, never observe beyond our cosmic horizonus, is not defeat. It is the setting of the greatest intellectual drama of our time. It is the cosmic whisper that we are part of something greater than our understanding, that we are players in a story written across light years and eons, one that may never reveal its final chapter, and yet one we are compelled to pursue with all the brilliance, creativity, and courage we can muster. The conflict is not just between theory and data, or between what is known and unknown. It is between our longing for certainty and the universe's refusal to offer it. And in that conflict lies not only the future of science, but the future of meaning itself. As our scientific understanding has expanded into realms once thought unknowable, the pursuit of the universe's edge, a metaphorical and scientific boundary between comprehension and mystery, has become the site of a profound and escalating conflict. This conflict is not one of hostility but of tension, of competing paradigms vying for dominance in the minds of cosmologists and physicists who seek not only to describe the cosmos, but to explain its origins, structure, and ultimate fate. At its core lies a fundamental question: is the universe finite or infinite? If finite, what lies beyond? If infinite, how do we define boundaries at all? The answers to these questions remain elusive, because they demand resolution not only from empirical evidence, but from deeply abstract theoretical frameworks that often contradict one another, exposing the cracks between observation and theory, between relativity and quantum mechanics, between what can be seen and what must be imagined. The roots of this tension trace back to the dichotomy between the two great pillars of 20th century physics, general relativity and quantum mechanics. General relativity, Einstein's elegant theory of gravity, gives us a universe that curves, bends, and stretches under the influence of mass and energy, describing phenomena such as black holes, cosmic expansion, and gravitational lensing with extraordinary precision. On large-scale galaxies, clusters, and the evolution of the cosmos itself, it is unmatched, yet it breaks down at the smallest scales. Unable to account for quantum effects at the heart of singularities or the chaotic fluctuations of the early universe, quantum mechanics, on the other hand, governs the subatomic world with uncanny accuracy, predicting outcomes with probabilistic precision and explaining the behavior of particles, forces, and energy fields at scales far too small for classical logic. But quantum theory has no place for gravity, and when pushed to explain the universe as a whole, it falters. The two frameworks refuse to unify cleanly, and yet the cosmos demands a union, a theory of everything that can describe both the curvature of space-time and the quantum foam from which it may have emerged. Within this unresolved schism, different interpretations of the universe's edge and of the cosmos itself have arisen. Some models, like the closed universe theory, propose that the cosmos is finite in size but unbounded, akin to the surface of a sphere. If you travel far enough in one direction, you return to where you started, never encountering an edge, but also never escaping the totality. Others suggest a flat, infinite universe, where expansion continues forever, space never curves back on itself, and the idea of a boundary is meaningless. Still others posit an open universe, where expansion is unbounded but curved in such a way that space-time thins out toward an unreachable horizon. Each of these models has supporters, and each is rooted in data. Measurements of the cosmic microwave background radiation, supernova luminosity, baryon acoustic oscillations, and the large-scale distribution of galaxies. Yet these observations are limited to the observable universe, a sphere defined by the light that has reached us since the Big Bang. Beyond that lies speculation. The universe may continue forever, or it may fold into a higher dimensional space, or it may end in a boundary we will never observe, possibilities grounded in math, yet untestable with current instruments. The conflict deepens when considering the role of inflation, a proposed period of exponential expansion in the early universe, during which quantum fluctuations were stretched to cosmic scales. Seeding the structure we see today, inflation solves many problems elegantly. It explains why the universe appears flat, why regions far apart have the same temperature, and why matter is distributed in a nearly uniform way. But inflation also implies something more radical: the idea that inflation never completely ends. In many models, as one region of space stops inflating and becomes a universe like ours, other regions continue to expand, spawning more pocket universes in an endless cascade. This leads to the multiverse hypothesis, in which our universe is just one of infinitely many, each potentially with its own physical laws and constants. While compelling to many theorists, the multiverse is deeply controversial. It stretches the definition of science itself, relying on entities we may never observe, and raises questions about predictability, falsifiability, and the role of probability in a universe of infinite outcomes. Some see it as the natural consequence of cosmological inflation and string theory. Others see it as a failure to constrain speculation with evidence. Simultaneously, cosmologists must grapple with observational anomalies that strain existing models. The expansion of the universe, once thought to be slowing due to gravity, is instead accelerating, driven by a mysterious force known as dark energy. The nature of this force remains unknown. Is it a property of space itself? Is it a new field? Does it vary over time? Current models, such as the Lambda CDM, cold dark matter with a cosmological constant, fit much of the data, but tensions persist. Measurements of the Hubble constant, the rate of cosmic expansion, differ when obtained from the early universe versus the local universe, suggesting either unknown systematic errors or cracks in the standard model. Other observations, such as alignments in the cosmic microwave background or potential anisotropies in large-scale structures, hint at asymmetries and features that shouldn't exist if the universe is truly isotropic and homogeneous on large scales. These could be flukes, errors, or the first signs of deeper truth echoes from before the Big Bang, perhaps, or imprints of other universes bleeding into our own. The struggle to define the edge of the universe is as much philosophical as it is scientific. What do we mean by edge? A boundary in space? A temporal limit? A limit to knowledge? Some theorists argue that the universe has no edge because space is infinite. Others suggest the edge is a boundary in time, beyond which our equations cannot reach the singularity of the Big Bang. Yet even the Big Bang may not have been the beginning, only a phase transition in a deeper eternal framework. Cyclic models propose an endless sequence of expansions and contractions, while quantum cosmology models suggest the universe tunneled into existence from a prior quantum state. In each case, the conflict returns. What is real, and what is mathematical extrapolation? What is evidence, and what is inference? Can we ever truly know the answer to a question that lies beyond the reach of light and time? Adding to the complexity are the philosophical divides within the scientific community itself. Some cosmologists adhere to empirical conservatism, arguing that we should focus only on what can be observed and measured, rejecting theories that cannot, in principle, be tested. Others embrace a more expansive view, suggesting that theoretical coherence, mathematical elegance, and explanatory power are valid criteria for scientific belief, even in the absence of direct observation. This division plays out in debates over the multiverse, string theory, quantum gravity, and the nature of time itself. It is a debate about the future of science. Should we push the boundaries of imagination and trust that technology and understanding will catch up? Or should we restrain ourselves to the known and the measurable, even if it means ignoring what might lie just out of reach? In the end, the conflict at the heart of modern cosmology is not simply between theories or data, is between visions of reality itself. One vision sees the universe as fundamentally understandable, governed by elegant laws that we are steadily uncovering, marching toward a final theory. The other sees the universe as a complex, possibly chaotic system, where observation is always partial, knowledge is always bounded, and some truths may lie forever beyond us. Both visions inspire, and both are supported by the same body of evidence, interpreted through different lenses. This is the paradox of our age. The more we learn, the more questions arise. The edge of the universe may never be a wall we can touch or a line we can cross. It may remain, always, a horizon receding as we approach, mocking our certainty, challenging our intellect, and reminding us that science, at its heart, is not just a catalog of facts, but a journey into the unknown, driven by the tension between what we believe and what we can prove. It is in this tension, in this conflict, that the future of cosmology will be written not as a final answer, but as an ever-unfolding story of light, darkness, and the human mind reaching beyond itself. If the universe has no edge, no boundary in space or time, no final frontier to mark the limit of existence, then everything we thought we were striving toward in our cosmic quest shifts. The very idea of arrival dissolves, replaced by a kind of eternal exploration without a final answer, a horizon that always retreats no matter how far we travel. For centuries, human beings have been driven by the belief that nature, though complex, is ultimately knowable, that the mysteries of the cosmos could be decoded, and that a grand, unifying theory and ultimate law might one day bring the universe fully into the light of reason. But the consequences of a universe without an edge strike at the core of that belief. It means there may be no whole to grasp, no complete picture to draw, only expanding portions of reality unfolding in front of us, like pieces of a puzzle that grows faster than we can solve it. This notion reshapes both the foundations of modern physics and the existential frameworks we construct around them. If the cosmos is infinite, or even just unknowably vast, then our models are provisional, by definition useful, insightful, but never final. The implication is humbling. Not that science is broken, but that it is permanently incomplete. that every discovery will inevitably give birth to more mysteries. From a scientific perspective, a universe without an edge demands a radical rethinking of the frameworks that have guided cosmology for the last 100 years. General relativity, which models gravity as the curvature of space-time, assumes a kind of order and continuity to the universe's structure. But infinite space challenges the assumptions baked into those equations show. Do you define curvature in a space that never ends? What happens to conservation laws in an infinite system where energy and mass cannot be counted in total? Similarly, quantum field theory, which underpins the standard model of particle physics, assumes a background space-time in which interactions happen if space is unbounded. Is the vacuum truly empty? Or does it teem with activity across dimensions we can't measure? Inflation theory complicates this even further. If eternal inflation produces an infinite multiverse, then the very idea of a typical universe breaks down. Probabilities become meaningless. Scientific prediction stumbles because the sample size is infinite and untestable. It means that our own universe, with its particular laws and constants, might not be a necessary outcome of deep principles, but simply one version among countless others, a cosmic accident floating in a sea of infinite possibility. Such a shift forces cosmologists to confront the limitations of their tools. Models that work beautifully within the observable universe falter when extended to the infinite. Simulations can't compute the behavior of space-time when the data points stretch beyond any imaginable boundary. Even the cherished notion of causality, where one event leads to another, can lose meaning in the face of infinite timelines, where every event may repeat in some form, somewhere, inevitably. The need for new physics becomes undeniable. The tension between quantum mechanics and general relativity must be resolved in a way that accommodates the full implications of an edgeless universe. String theory, loop quantum gravity, and other approaches aim to describe a quantum geometry of space, where the grainy, probabilistic nature of the microscopic world blends with the smooth curvature of the macrocosmic. But so far, none have produced a final, testable model. Theoretical physicists speak of the need for a paradigm shift, to conceptual revolution, akin to the move from Newton to Einstein, that might reframe not just how we model the universe, but what we believe it is. The philosophical consequences of this are no less staggering. If the universe has no edge, then it may also have no centerno-privileged place, no absolute scale. Humanity, already removed from the center by Copernicus and Darwin and Hubble, now finds itself adrift in a cosmos without boundaries, a speck not only in size but in significance. Yet with that realization comes a strange kind of liberation. If there is no center, then we are just as central as any other point. If the universe is infinite, then our consciousness, finite and fleeting though it may be, is not meaningless, but miraculous. That it can arise at all, even once, even here, is profound. In a cosmos where everything that can happen might happen, our experience becomes a moment of awareness in a sea of blind unfolding. We are the edge. We are the place where the universe wakes up and looks at itself. However briefly, the existential weight of this view is heavy. For some, it suggests nihilism. If the universe is endless and indifferent, then what does anything matter? But for others, it invites a deeper kind of meaning, not one imposed from above, but one we create ourselves, in defiance of entropy, in celebration of perspective, in awe of the mystery that surrounds us. If the universe has no edge, it also has no final truth, only evolving approximations. Science becomes a kind of storytelling, grounded in data but shaped by imagination, forever provisional, forever expanding. This doesn't weaken science, it elevates it. It means the role of the scientist is not to possess truth, but to chase it with clarity, humility, and courage. The same is true for all of us. We are explorers in an unending sea, and the journey is not about reaching a shore, but about what we become in the sailing. That requires a new intellectual posture that embraces uncertainty not as failure, but as freedom. It means rethinking education, shifting from memorization to inquiry. It means encouraging interdisciplinary exploration, where physics meets philosophy, where math meets meaning. It means building tools not just to measure the universe, but to engage with it emotionally, spiritually, poetically, Because when the universe is infinite, so too are the ways we can relate to it. The consequences also ripple into practical realms. If we accept that our models are limited to the observable universe, then we must design new missions and instruments with that humility in mind. We must ask what it means to measure a cosmos we can never fully see. Should we prioritize mapping the cosmic microwave background in more detail, searching for subtle signs of curvature or topology that might hint at the global structure? Should we invest in more powerful gravitational wave observatories, hoping to hear whispers from epochs we can't see? Or should we reframe our questions entirely, focusing on the nature of information, on the limits of knowledge, on the relationship between observer and observed? These are not idle questions. They shape funding, research agendas, the direction of science itself. The absence of an edge is not just a theoretical curiosity, it is a constraint on how we define progress. Culturally, the implications are just as profound. If the universe has no edge, then perhaps neither do human potential, creativity, or resilience. The metaphor extends. Just as the cosmos expands beyond measure, so too can our compassion, our insight, our sense of belonging. The infinite universe becomes a canvas on which we paint meaning, not because the universe requires it, but because we do. And in doing so, we honor the mystery. We participate in it. We give voice to the silent dark. We are the paradox-finite beings in an infinite space, seeking truths that may never be fully known, yet drawn forward by the very impossibility of the task. And that is the true consequence of the conflict, not despair, but transformation. The edge we sought was never a place, but a process. Not a line to cross, but a realization. That understanding is not a destination, but a practice. That wonder is not the beginning of knowledge, it is the result. And in that wonder, we find the strength to keep going. So what if the universe has no edge? Then we live in an endless unfolding, a story with no final chapter, a dance that never concludes. Then our science is a song, our questions the rhythm, our discoveries the melody. Then our meaning is not given but chosen. And in a cosmos without boundaries, that choice is everything. Because we are not separate from the universe, we are a function of it. We are the way it knows itself. And that means the journey matters more than the destination. The conflict may never end, but neither will the beauty, neither will the questions, neither will the light. There are moments in scientific history when the trajectory of human understanding shifts dramatically, when an observation, a theory, or a technological leap redefines what we thought was possible and pushes the edge of knowledge farther into the unknown. In cosmology, these moments are rare, but when they happen, they mark turning points not just in science, but in the human story. And in recent decades, we've stood at the edge of several such turning points realizations that have not only transformed our view of the universe, but have fundamentally changed the questions we ask about existence itself. Among the most significant of these was the discovery that the universe is not just expanding, but accelerating in its expansion, a finding that shattered long-held assumptions and introduced one of the most mysterious forces in all of physics: dark energy. The year was 1998. Two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, had been observing distant Type Ia supernovae stellar explosions that serve as standard candles for measuring cosmic distances. The expectation was straightforward. If the universe's expansion had been slowing due to gravity since the Big Bang, then distant supernovae should appear slightly brighter than predicted by a constant rate model. Instead, they were dimmer, much dimmer. This was not an error or an anomaly, it was a revelation. The expansion of the universe was not slowing down, it was speeding up. Some unknown force, was counteracting gravity on the largest scales and pushing galaxies apart with increasing velocity. That something was named dark energy. The implications of this discovery were staggering. First, it meant that the fate of the universe was not one of gentle coasting or eventual collapse, but of endless acceleration, a cold, dark future in which galaxies recede beyond each other's reach, stars burn out, and matter decays into a sea of entropy. Second, it revealed that everything we could, sea stars, galaxies, nebulae, even dark matter, was only a small fraction of what actually exists. Dark energy accounts for nearly 70% of the total mass energy content of the universe. Yet we have no clear understanding of what it is. Is it a property of space itself, described by Einstein's cosmological constant? Is it a dynamic field, like quintessence, that changes over time? Could it be a sign that our understanding of gravity is incomplete on cosmic scales? Whatever the answer, dark energy represents not just a new term in the equations, but a fundamental shift in how we understand reality. Alongside dark energy, another pillar of modern cosmology has come to define this turning point: the recognition of dark matter. First inferred from galaxy rotation curves by astronomers like Vera Rubin, and later supported by gravitational lensing and large-scale structure simulations, dark matter explains why galaxies hold together, why clusters form, and why the cosmic web has the shape it does. It does not emit or absorb light. It interacts with regular matter only through gravity, and it remains invisible to even our most sensitive instruments. Together, dark matter and dark energy dominate the cosmos. Their existence tells us that the universe is governed by forces and components we have yet to truly understand, that the standard model of physics, while powerful, is incomplete. The search for the particles or fields responsible for dark matter has led to the construction of massive underground detectors, particle accelerators, and ambitious space missions. And though we haven't yet found the smoking gun, every null result tightens the constraints and guides us toward the truth. This is where technology becomes the key. Every major breakthrough in cosmology has been enabled by advances in how we observe the universe. From Galileo's first telescope to the mountaintop observatories of the 20th century, our vision has expanded with our instruments. But it was the launch of the Hubble Space Telescope in 1990 that marked a new era. Floating above Earth's atmosphere, Hubble gave us crystal-clear images of galaxies billions of light-years away. It allowed us to measure the rate of expansion more precisely, to glimpse the early universe, and to witness phenomena like gravitational lensing, nebula formation, and galactic collisions with unprecedented clarity. Hubble's legacy is more than just images. It's a transformation in how we experience the cosmos. It made the universe personal, visual, immediate, and it prepared us for what came next. Enter the James Webb Space Telescope. Launched in late 2021 and positioned at the Earth-Sunday L2 Lagrange point, with a mirror over 6 times the size of Hubble's and instruments optimized for infrared observations, Webb is designed to see further and detect the faint glow of the first stars and galaxies, to analyze the atmospheres of exoplanets, and to peer into stellar nurseries where new solar systems are born. In just its first year of operation, Webb delivered jaw-dropping results. Galaxies forming less than 400 million years after the Big Bang, some larger and more structured than models had predicted. Direct spectra of exoplanet atmospheres showing carbon dioxide, water vapor, and potentially organic molecules. Intricate details of planetary systems, nebulae, and distant quasars that challenge our assumptions about how galaxies and stars evolve. These findings don't just fill in gaps, they rewrite textbooks. They challenge timelines, test our simulations, and force us to reconsider what's possible. Other telescopes, like the Event Horizon Telescope, which imaged the shadow of a black hole for the first time in 2019, and gravitational wave observatories like LIGO and Virgo, have added even more layers to this revolution. We can now hear the universe in gravitational waves, ripples in space-time caused by massive events like black hole mergers and neutron-star collisions. These signals, once thought undetectable, are now a routine part of astronomy, giving us an entirely new way to study the cosmos. They allow us to probe the nature of compact objects, test general relativity in extreme conditions, and perhaps one day detect the whisper of inflation itself. Together, these technological achievements have pushed us into a new era turning point, not marked by a single discovery, but by a cascade of insights that reshape the field. We now study the universe not just in visible light, but in the full electromagnetic spectrum, in neutrinos, in cosmic rays, in gravitational waves. We build sky surveys that catalog billions of galaxies, map the structure of dark matter, and measure the distortions of space-time itself. The tools we've built: the Large Hadron Collider, the Vera-C, Rubin Observatory, the Square Kilometer Array, not just machines. They are extensions of human curiosity, designed to extract meaning from the noise of the cosmos. And what is the meaning of all this? Why does this turning point matter? Because it represents the moment when humanity's vision caught up with its ambition. For generations, we asked where the universe came from, how it works, what it's made of. Now we're beginning to answer those questions, not completely, not finally, but with clarity and precision unimaginable just decades ago. We have identified the building blocks of cosmic structure, measured the geometry of the universe, and traced the evolution of matter from the first microseconds to the present day. And yet, even in this moment of triumph, the universe reminds us how little we truly know. Dark energy, dark matter, the quantum nature of gravity, the origin of time, the possibility of a multiverse. These are not footnotes, they are the main narrative of the next chapter. And they point to one undeniable truth. We are at the threshold of a new understanding. This turning point is not an end, it is a beginning. A new generation of scientists, thinkers, and dreamers is rising to the challenge, building on the foundation laid by centuries of inquiry. They are not content with static models or accepted truths. They ask deeper questions, push harder boundaries, and embrace the unknown with a blend of skepticism and wonder. They know that the cosmos is not a solved puzzle but a living question, and that every answer carries within it the seeds of the next mystery. This is what defines a turning point, not just new data or new theories, but a shift in the way we think, the way we look, the way we relate to the universe. And so we move forward not because we must, but because we are compelled. Compelled by curiosity, by beauty, by the impossible vastness of a universe that keeps unfolding no matter how far we reach. We are no longer just passive observers, we are participants in a cosmic story still being written. The turning point is here, and from it flows the next great journey, not to the edge of the universe perhaps, but into the depths of understanding, where every revelation becomes a mirror, every discovery a window, and every question an invitation to continue. For centuries, we've asked questions about the universe from a specific perspective and grounded in our senses, our place on Earth, our scale of time, and our classical understanding of space. We imagined the universe as a vast arena, an empty stage on which planets, stars, and galaxies move, governed by laws that could eventually be uncovered and mastered. But what if that very framework, how we look at the problem, is flawed? What if the nature of space, time, and matter is so radically different from our assumptions that our current models, elegant and useful as they are, can only ever be approximations? This is the crux of a growing realization in physics and cosmology, that a shift in perspective might be not just helpful, but necessary to move forward. And at the heart of this shift lie revolutionary ideas like the holographic principle, emergent space-time, and quantum gravity frameworks that challenge everything we thought we understood about what the universe is and how it works. Take the holographic principle, for example. At first glance, it sounds like science fiction. The idea that everything we experience in 3 dimensions, including time, might actually be encoded on a 2-dimensional surface, much like a hologram. But this concept is rooted in deep theoretical physics and has been taken seriously by some of the world's most respected scientists. It originated in the study of black holes. In the 1970s, physicist Jacob Bekenstein proposed that the amount of information, or entropy, inside a black hole wasn't proportional to its volume as one might expect, but to the area of its event horizon. Stephen Hawking later supported this with his discovery of black hole radiation, suggesting that black holes are not eternal and that their surface area corresponds to their thermodynamic entropy. The deeper implication? If the information content of a volume of space can be encoded on its surface, then perhaps the entire universe works this way. In the 1990s, physicist Leonard Susskind and Nobel laureate Gerard de Hooft developed this idea further, leading to the holographic principle, which was given mathematical weight through the AD-S-CFT correspondencia, a duality proposed by Juan Maldacena that showed how a theory of gravity in a higher dimensional space could be equivalent to a quantum field theory without gravity in a lower dimensional boundary. The implications of the holographic principle are profound. It suggests that what we perceive as space and time might be emergent phenomena, not fundamental ingredients of the universe, but byproducts of deeper information-based processes. In this view, gravity itself may not be a force in the traditional sense, but a manifestation of entropic relationships between pieces of quantum information. The fabric of spacetime could be an illusion, a large-scale effect of quantum entanglement patterns too small to see but essential to the structure of reality. This challenges the traditional goal of physics. Rather than describing the motion of objects through space, we may need to describe how space itself arises from more fundamental data. And if space is emergent, then so too might be time, a concept even more destabilizing. Could the flow of time, the division between past and future, be nothing more than a macroscopic effect of deeper symmetries or information loss? Could the arrow of time exist only because of the way entropy behaves in our observable patch of the cosmos? This shift in viewpoint away from objects and toward information has gained traction in part because of the role of quantum mechanics in shaping cosmic structure. Quantum theory, once confined to atoms and subatomic particles, is now seen as critical to understanding the largest structures in the universe. The early universe was a quantum system. Its tiny fluctuations, stretched by inflation, became the seeds of galaxies, clusters, and voids. These fluctuations were not deterministic. They were probabilistic, governed by uncertainty and entanglement. This means that quantum behavior didn't just give rise to matter, it shaped the entire structure of the cosmos. And if quantum principles can define what exists on the largest scales, then perhaps the fundamental description of the universe must be quantum from the beginning. But here lies the problem. Our current frameworks, quantum mechanics and general relativity, describe reality in incompatible ways. One is discrete, probabilistic, and defined by operators on a Hilbert space. The other is continuous, deterministic, and defined by smooth geometry. This divide has led many physicists to believe that neither theory is complete. What we need is not just a unification, but a reframing, a new language in which both gravity and quantum behavior are natural consequences of deeper principles. Alternative theories have begun to emerge, each attempting to shift the viewpoint in its own way. Some, like loop quantum gravity, aim to quantize spacetime itself, describing it as a network of discrete loops of information. Others, like causal dynamical triangulations, build spacetime from evolving geometric building blocks. More speculative frameworks, like emergent gravity or entropic gravity, propose that gravity is not fundamental, but thermodynamic. And then there's the bold idea of timeless physics, where time is not a basic parameter, but a relationship between events encoded in correlations. These approaches vary in detail, but they share a core insight that the universe may not be what it seems, that the things we observe, particles, fields, even space and time, might be projections, approximations, or emergent behaviors. This doesn't mean they're not real, but that their reality might be like the surface of a lake, visible, measurable, but dependent on deeper, invisible processes beneath. Changing our perspective also reshapes how scientific discussions unfold. In the classical model, a theory is either right or wrong, confirmed or falsified. But in this new landscape, theories may be complementary, different ways of describing the same underlying reality. The wave-particle duality of quantum mechanics taught us that nature can behave in multiple, seemingly contradictory ways depending on how we observe it. The same might be true for cosmological models. Perhaps the universe can be both finite and infinite, depending on the framework. Perhaps different mathematical structures describe the same physical world from different angles, like different maps of the same terrain. This shift requires humility. It means letting go of the desire for a single, final answer. It means embracing ambiguity, paradox, and metaphor as part of science, not signs of failure. But most importantly, this shift expands our sense of what science can be. It invites collaboration between disciplines. Physicists are increasingly working with computer scientists, philosophers, neuroscientists, and mathematicians to explore questions of emergence, complexity, and information theory. Concepts from thermodynamics, topology, category theory, and even linguistics are finding their way into cosmology. The boundaries between fields are dissolving, just as the boundaries of space itself are being redefined. We are no longer asking simply what the universe is made of. We are asking how it knows what to be, how information organizes itself into matter, how consciousness arises from neurons, how laws arise from chaos. These are questions at the edge of science and philosophy, and they demand a shift not just in method, but in mindset. The role of quantum mechanics in this transformation cannot be overstated. Once considered a theory of the very small, quantum mechanics is increasingly seen as the bedrock of reality, a framework not confined to particles, but underlying everything from the structure of space-time to the behavior of black holes. Entanglement, once a curiosity, now appears central to the fabric of the cosmos. Recent research suggests that the very connectivity of space, the fact that one region of space can relate to another, may be due to quantum entanglement. In other words, the geometry of the universe could arise from the information-sharing patterns of quantum systems. This idea, known as it from qubit, is gaining traction. The notion that space-time, matter, and forces all emerge from the quantum correlations of basic informational units. If true, then understanding the universe may not require more powerful telescopes, but more refined mathematics, new ways to model entanglement, coherence, and computation. This new perspective also reframes the question of the edge of the universe. In classical cosmology, we seek an edge in space, a boundary, or an endpoint. But in the quantum information view, the edge may be a limit of representation, not of existence. The question becomes, how is reality encoded? What rules govern the translation of quantum states into classical experience? Could the observable universe be a slice of a larger informational system, like a screen showing only part of a simulation? These questions sound radical, but they stem from careful reasoning, not fantasy. Theoretical physicists aren't giving up on reality, they're trying to understand why it appears the way it does. In the end, the shift in perspective is not about discarding what we know it's about, expanding how we think. The universe may not be a thing to be measured, but a process to be interpreted. Space may not be a container, but a relationship. Time may not be a flow, but a structure. And knowledge may not be about finding the ultimate law, but about navigating the layers of emergence, from the quantum to the conscious. This is not the end of science, it is its rebirth. A renaissance of imagination, grounded in precision, open to paradox, and driven by wonder. As we stand on the threshold of this new perspective, we are reminded that every breakthrough begins with a question not just about nature, but about ourselves. Are we looking at the problem the right way? Or is it time to turn the mirror inward and see the cosmos not just as it is, but as it is reflected through us? In that reflection, perhaps, we will find not just answers, but a new way to ask the question. There comes a moment in every great story when the world turns upside down, when everything the characters thought they knew is challenged by a truth so alien, so startling, that it forces them to look at everything with new eyes. In the story of the universe, that moment may already be happening. It isn't just one discovery, one theory, or one shift. It's the growing realization that our most basic assumptions about reality may be incomplete or even wrong. For centuries, we assumed the universe was singular, stable, and governed by elegant, discoverable laws that applied uniformly everywhere. We believed that with enough observation, theory, and time, we could explain everything from the motion of stars to the nature of consciousness. But now, as our tools grow sharper and our questions deeper, the edges of that worldview are fraying. The universe may not be a singular, understandable entity. It may be one of many. Or it may be a simulation. Or it may not be a thing at all, but an emergent experience produced by a deeper substrate of information, computation, or even mind. These aren't fringe ideas anymore. They are serious, mathematically sound, and increasingly necessary to explain observations that don't fit neatly within the traditional models. And in this unexpected twist lies perhaps the most important revelation of all, not just about the cosmos, but about ourselves. It began, as many revolutions do, with anomalies. Observations that didn't fit, parameters that seemed unnaturally tuned, forces like dark energy and dark matter that couldn't be detected. only inferred. When the cosmic microwave background radiation was mapped in greater detail, tiny irregularities appeared, cold spots and alignments that some scientists believe could point to interactions with other universes. When the Higgs boson was discovered, its mass was found to be suspiciously low, suggesting that some protective mechanism was keeping the universe stable against quantum collapse. And when physicists studied the constants of nature, strength of gravity, the charge of the electron, the cosmological constant itself, they found that these values seemed improbably precise, as if tuned for life. If any of them were slightly different, stars wouldn't form, chemistry wouldn't work, and observers like us wouldn't exist. Was this coincidence? Was it divine design? Or was it something else, something bigger? Enter the multiverse. Once dismissed as speculative fantasy, the idea of a multiverse has gained serious traction in both theoretical physics and cosmology. There isn't just one version of the multiverse, but many, each emerging from a different context. The cosmological multiverse arises from eternal inflation. In this model, different regions of space stop inflating at different times, forming bubble universes with different physical constants. While the background continues to expand, string theory's landscape adds another layer, predicting as many as 10 circumflex 500 possible solutions to its equations, each corresponding to a different universe with its own laws of physics. Then there's the quantum multiverse, based on the many worlds interpretation of quantum mechanics, in which every quantum event spawns a branching universe for every possible outcome. Each of these models is complex, mathematically rigorous, and deeply unsettling, because they suggest that our universe totality of everything we can see is just one tiny slice of a much larger, perhaps infinite, reality. In a multiverse, our universe is not special. Its laws are not universal. Its fine-tuned constants are not designed, but selected like one winning lottery ticket among trillions of possibilities. This view reframes everything. In a multiverse, the question isn't, why is the universe the way it is? But why are we in this one? It's a selection effect, known as the anthropic principle. We observe the universe to be life-friendly, because if it weren't, we wouldn't be here to observe it. This idea, though logically sound, deeply challenges the classical scientific approach, which seeks causal explanations for everything. The multiverse defies that demand. It suggests that some things, like the values of physical constants, may be accidents, irreducible to deeper laws. That's hard to swallow. It shifts science toward a statistical, existential framework, where understanding means knowing our place in a vast landscape, not uncovering a universal truth. And while the multiverse remains unconfirmed, perhaps unconfirmable, is increasingly seen not as a wild guess, but as the most coherent extension of current theories. But the surprises don't stop there. As we probe deeper into the nature of reality, another idea has emerged that's even more radical than the multiverse: the simulation hypothesis. Proposed most famously by philosopher Nick Bostrom in 2003, the simulation hypothesis argues that if it's possible for a sufficiently advanced civilization to simulate entire universes complete with conscious beings, then it's statistically likely we are living in one. The reasoning is simple. If simulations are possible, then they are likely to be numerous. And if simulated beings cannot tell they are simulated, then the chances we are the original version are vanishingly small. What makes this idea more than philosophy is the growing alignment between physics and computation. The universe behaves like a computational system. Space is discrete. Time moves in quantized steps. Physical laws can be expressed as algorithms. Information cannot be destroyed. Black holes behave like data processors. Quantum entanglement resembles error correction codes. Some physicists have even proposed that space-time itself emerges from quantum bits of information, processed in a network beyond the reach of classical measurement. If the universe is a simulation, then everything changes. The laws of physics become software. The constants of nature become configurable parameters. And the edge of the universe might not be a spatial boundary, but a computational limita resolution, beyond which no further detail exists. The simulation hypothesis doesn't mean our experiences are fake, it means reality is real, but fundamentally informational. It suggests that consciousness and perception may be more central to the structure of the universe than previously believed. This idea aligns with certain interpretations of quantum mechanics, where observation plays a key role in collapsing wave functions and creating definite outcomes. It also dovetails with ancient philosophical traditions like those of Vedanta and Buddhism that see reality as a projection of mind, a kind of cosmic dream unfolding in layers of awareness. Of course, both the multiverse and the simulation hypothesis are controversial. They raise deep philosophical and scientific questions about testability, falsifiability, and the meaning of evidence, but they are not without support. Major figures in physics Stephen Hawking, Max Tegmark, Sean Carroll, David Deutschhoff all explored these ideas seriously. Experiments are even being proposed to test aspects of the simulation theory, such as detecting limits in cosmic rays that could point to an underlying lattice structure. Whether these tests will yield answers is unknown, but the fact that we're asking the questions at all signals a deeper change. We are no longer content with classical models. We are reaching for something more fundamental, not just laws, but meta-laws. Not just equations, but contexts. This, perhaps, is the true unexpected twist, not that the universe is stranger than we thought, but that it may be stranger than we can think, that our place in the cosmos is not central, but participatory, that we may be part of a system far more vast, more complex, and more layered than we ever imagined. That the search for knowledge is not a journey toward certainty, but a spiral into deeper and deeper wonder. We are not outside observers of the universe. We are within it, of it, and possibly created by it in ways we have yet to grasp. Our consciousness, our science, our stories all may be reflections of a deeper logic, an algorithmic order unfolding beneath the surface of appearances. In that realization lies a new kind of humility and a new kind of courage. It means the universe may never be fully knowable in the classical sense, but it also means that meaning, creativity, and imagination are not luxuries. They are essential tools in our effort to navigate this mystery. The unexpected twist is not the arrival of an answer, but the unveiling of a question so vast it stretches the limits of language. And in the face of that question, we are not helpless. We are alive, awake, and aware. We are storytellers in a simulated multiverse, physicists in a holographic dream, particles that wonder about their own origins. And that wonder, that capacity to ask, to imagine, to reach beyond us, what makes us not just observers of the universe, but expressions of it. In the end, the twist is not that we are small, but that we are capable of understanding our smallness, that we can hold infinity in our minds, that we can gaze into the cosmic dark and find not fear, but a fire of curiosity. The multiverse may be real. The simulation may be real. The universe may have no edge. But we are here. We are thinking. And the mystery is only beginning. As breathtaking as our journey through the cosmos has been marked by revolutionary discoveries, paradigm-shifting theories, and technological triumphs, there remains a sobering truth at the heart of modern cosmology. Many of our deepest questions are still unanswered. We have come far, farther than anyone could have imagined just a century ago. Yet we now face challenges of a new magnitude. These challenges are not only technical or logistical, but conceptual. We are entering a phase where the complexity of the universe demands tools we have not yet built, theories we have not yet imagined, and collaborations that stretch across nations, disciplines, and even philosophies of science. The edge of our knowledge is no longer just a matter of what we don't know. It's about how we even go about knowing. And so the horizon of future research is both inspiring and daunting. To move forward, we must confront the limitations of our current tools, reimagine the infrastructure of exploration, and develop bold strategies to reach deeper into the unknown. One of the most immediate hurdles is observational limitation. Despite the astonishing capabilities of modern telescopes like Hubble, Chandra, and the James Webb Space Telescope, JWST, we are still restricted by the finite speed of light and the opacity of the early universe. We cannot see beyond the surface of last, scattering the moment when the universe became transparent, about 380,000 years after the Big Bang. The cosmic microwave background, CMB, is the oldest light we can detect, And beyond that, our universe is a fog of plasma that no photon can traverse. To study what happened before that moment during inflation, or at the instant of the Big Bang, we need to find alternative messengers. Gravitational waves, neutrinos, and the elusive patterns of primordial quantum fluctuations may hold the key, but detecting these signals at the necessary sensitivity is enormously difficult. Gravitational wave detectors like LIGO and Virgo have opened a new observational window, but they are still in their infancy. The signals they detect are strong, but relatively recent. Detecting the faint, stretched-out gravitational waves from the very early universe, so-called primordial wave swill, require detectors like LISA, the Laser Interferometer Space Antenna, which will operate in space, free from terrestrial noise, and capable of measuring lower frequency waves that Earth-based detectors miss. Another limitation is resolution and depth. Even with JWST's infrared capabilities, there are limits to how far we can see, how clearly we can resolve distant galaxies, and how precisely we can measure the composition of exoplanet atmospheres. To reach further, we need larger mirrors, more sensitive detectors, and new approaches to imaging. Concepts like the LUVOIR, Large UV, Optical, IR Surveyor, and HABEX, Habitable Exoplanet Observatory, represent the next generation of space telescopes, massive instruments capable of directly imaging Earth-like exoplanets, mapping the large-scale structure of the universe in exquisite detail, and possibly detecting biosignatures of alien life. These missions are still in the conceptual or planning stages, and their realization will require not just engineering breakthroughs, but sustained political and financial support. Building them will be one of the most ambitious scientific projects in human history, demanding international cooperation and decades-long commitment. Beyond technical hurdles, future research must grapple with conceptual challenges. As we probe deeper into questions of dark energy, dark matter, and the unification of quantum mechanics and gravity, we are reaching the limits of our existing theoretical frameworks. The standard model of particle physics, while extraordinarily successful, does not include gravity. General relativity, while powerful, cannot be quantized in the traditional sense. The search for a quantum theory of gravity remains the holy grail of theoretical physics, and it is one that has so far eluded us. String theory, loop quantum gravity, and emergent gravity are promising contenders, but none have produced testable predictions that can be verified with current experiments. Progress in this domain may require not just more data, but new thinking, perhaps even a reconceptualization of what physics is. Are space-time and matter truly fundamental? Or are they emergent properties of a deeper, information-based reality? Can we reconcile the non-locality of quantum entanglement with the locality of classical fields? These questions cut to the core of what reality is and how we understand it. Another major challenge is data analysis and interpretation. The sheer volume of data generated by modern telescopes and simulations is staggering. Projects like the Vera-C Rubin Observatory will generate tens of terabytes of data every night. Sorting, analyzing, and interpreting that data requires advanced machine learning, new algorithms, and collaborative frameworks that go beyond traditional scientific publishing. The field of astroinformatics is rapidly growing, but keeping pace with the data tsunami is an ongoing struggle. Future scientists will need to be not only physicists and astronomers, but data scientists, computer engineers, and systems thinkers. The integration of artificial intelligence into the scientific process is already underway, and it promises to reshape how discoveries are made, not by replacing human intuition, but by augmenting it, revealing patterns and anomalies that might otherwise go unnoticed. Then there is the problem of access and inequality. The frontier of cosmology is increasingly defined by massive, expensive projects that only the wealthiest nations or consortia can afford. This creates a disparity in participation and opportunity. To truly unlock the secrets of the universe, we need a global science network of thinkers, dreamers, and builders from every corner of the Earth. Future missions must be inclusive, not only in terms of geography, but also gender, culture, and discipline. The questions we face are too big to be answered by any one nation or group. They require a planetary effort, grounded in shared curiosity and collective wisdom. Despite these challenges, scientists are not deterred. On the contrary, There is a palpable sense of excitement in the field, a feeling that the next breakthroughs are within reach. Plans are already underway for missions that could revolutionize our understanding of cosmic inflation, the birth of galaxies, and the nature of dark matter. The European Space Agency's Euclid mission and NASA's Roman Space Telescope will conduct deep sky surveys to map the geometry of dark energy. Ground-based experiments like the Simons Observatory and CMBS-4 will study the polarization of the cosmic microwave background with unprecedented precision, searching for clues about the earliest moments of the universe. Particle physics will continue to explore beyond the Standard Model, with future colliders proposed to reach energies that might reveal supersymmetric particles or hidden dimensions. Meanwhile, cross-disciplinary collaborations are flourishing. Cosmologists are working with quantum information theorists to explore the holographic nature of space-time. Mathematicians are developing new tools to model higher dimensional spaces. Philosophers of science are engaging with physicists to refine the logic and language of cosmological argument. And young researchers, raised in the digital era, are bringing fresh eyes and new tools to ancient mysteries. What does this all mean for the future? It means that the golden age of cosmology is not behind use, it is just beginning. We are no longer content to ask where the stars are or what they're made of. We are asking what space is, what time is, what reality is, and we are building the instruments to find out. But it won't be easy. The hurdles are real. They include not just technical challenges, but human ones. Patience, cooperation, humility, and vision. We must fund the missions, educate the next generation, protect the night sky from satellite pollution, and ensure that science remains a shared global enterprise. Above all, we must remember why we do this. Not for profit, not for prestige, but because we are beings of curiosity, born into a universe that invites us to wonder. The challenges we face are steep, but the questions we ask are worth it. What happened before the Big Bang? What is the fate of the universe? Are we alone? Is the cosmos infinite? Are we living in a simulation? These are not idle questions. They are the heartbeat of a civilization reaching outward, upward, and inward. And so we press one eyes to the sky, minds open, hearts full of questions. The universe is still speaking, and we are learning, slowly, how to listen. We are now living in a time where the pursuit of the universe's ultimate truth has never been more energized, nor more fragmented. For every scientific breakthrough, there arises a competing interpretation. For every new observation, a dozen theories rise to explain it, each with their own strengths, elegance, and glaring gaps. It is not chaos, it is confrontation. A final confrontation of ideas at the frontier of knowledge. The competing theories that now define cosmology aren't merely academic exercises. They are radically different visions of what reality is, how it operates, and what lies beyond the veil of the observable. And at the center of this intellectual battle lies the question that has haunted physicists for over a century. Can we unify the strange probabilistic world of quantum mechanics with the smooth and deterministic flow of general relativity? Can we bridge the cosmic and the quantum into one coherent framework? Or are we forever doomed to choose between models that work beautifully in isolation, but crumble when brought into the same room? On one side of this cosmic battleground stands string theory, the longest-running and most mathematically rich attempt to unify the laws of physics. String theory posits that the fundamental building blocks of the universe are not zero-dimensional particles, but one-dimensional strings vibrating at different frequencies. These vibrations determine the properties of particles' mass, charge, spin, and allow gravity to be described within a quantum framework. The theory naturally requires extra spatial dimensions, typically 10 or 11, which are thought to be compactified beyond the reach of current observation. One of string theory's greatest strengths is its ability to include gravity in a quantum context, something no other framework has achieved with such mathematical consistency. It also led to the AD-S-CFT correspondence, a duality that connects gravitational theories in a curved space with quantum field theories on a lower dimensional boundary, arguably the most concrete realization of the holographic principle. Yet string theory's greatest weakness is its lack of testability. With no experimental evidence for strings, supersymmetry, or extra dimensions, critics argue that string theory may be more philosophy than physics, a beautiful idea, with no measurable consequences, at least for now. Opposing it, yet equally ambitious, is loop quantum gravity, LQG. Instead of positing strings or extra dimensions, LQG takes a more conservative path. It quantizes space itself. In this theory, space is made up of tiny loops woven into a Fabrice loop, representing a quantized unit of area or volume. Time too becomes granular. The result is a picture of space-time as discrete, not continuous, with no background stage upon which events unfold. LQG avoids many of the abstract assumptions of string theory and works directly with the geometry of general relativity, trying to preserve its core while translating it into quantum language. It has produced testable predictions, such as potential signatures in the polarization of the cosmic microwave background or the modification of black hole evaporation. But LQG struggles with unification. It doesn't naturally include the particles and forces of the standard model, and it's not yet clear how it would describe the universe on large scales or explain inflation. The theory remains incomplete, a compelling sketch rather than a finished portrait. Then, there are the emergent gravity models, perhaps the most radical departure from classical assumptions. In these theories, gravity isn't fundamental at all. It emerges from deeper principles of entropy, thermodynamics, and information theory. Pioneered by thinkers like Eric Verlinde, emergent gravity proposes that what we perceive as space-time curvature is a result of underlying statistical processes like temperature arising from the motion of molecules. This perspective is aligned with the holographic principle, which suggests that all of the information in a volume of space can be encoded on its boundary. If true, this would mean that our 3D reality is a projection from a deeper 2D information structure. These ideas resonate with the growing belief that information, not matter or energy, may be the most fundamental element of the universe. The strength of these theories lies in their novelty and their potential to explain dark matter or the accelerated expansion of the universe without new particles. But they remain highly speculative and are difficult to test in practice. Overlaying these theoretical frameworks is the deeper, existential debate. Will we ever find a true boundary to the universe, to our knowledge of it? From the classical Big Bang model, which implies a temporal boundary at the beginning of time, to eternal inflation and multiverse theories that remove that beginning entirely, the debate rages on. Some models propose a cyclic universe, where expansion and contraction repeat indefinitely, erasing the need for a beginning or end. Others suggest that time is emergent, a relational property that arises only in certain conditions and may not exist at all before the universe. Some argue that the Big Bang is not the beginning, but a bounce from a prior contracting state. But every theory comes up against the same challenge: the limits of observability. We are confined to our cosmic horizon. We cannot see beyond the CMB. We cannot test what came before time. This fuels the notion that our theories may reach a boundary not in space, but in epistemology. Some physicists accept this and embrace the multiverse as the best explanation for fine-tuning. Others reject it as untestable and unscientific. The tension is not just physical, it is philosophical, epistemological, even cultural. Are we seeking truth, or are we constructing models that fit what we can see? Despite the conflict, real progress is being made. Unifying physics remains the central challenge of the field, and promising bridges are being built. The holographic duality between gravity and quantum field theory provides a powerful hint that these two realms are not incompatible, but intimately connected. The study of black hole thermodynamics, including recent work on the black hole information paradox and the firewall debate, is sharpening our understanding of how quantum information behaves in curved spacetime. Quantum cosmology, including theories like the Hartle-Hawking no-boundary proposal, is probing what a quantum beginning of the universe might look like. The discovery of gravitational waves, the imaging of a black hole, and the deep field views from JWST are not just scientific milestones, they are empirical constraints that all theories must now answer to. The future of cosmology lies in this confrontation. It will not be a singular event, but an ongoing refinement, a creative tension between models, data, and imagination. It will depend on new tools. Next, generation space telescopes like LUVOIR, missions like LISA, particle accelerators beyond the Large Hadron Collider, and precision observatories. that measure the universe with unmatched resolution. It will depend on new minds. Theorists willing to think beyond Einstein and Newton, observers patient enough to mine deep data, philosophers able to challenge the very language of science. It will also depend on the humility to accept that some truths may always remain beyond our reach, and the courage to keep reaching anyway. This final confrontation is not a clash of weapons, but of paradigms. It is not a war of ideas, but a synthesis, a slow, grinding emergence of new understanding from the friction of disagreement. In the end, we may not find a boundary to the universe. We may find instead a boundary to the way we've been asking the question. And in crossing that boundary, we may discover not just a new theory, but a new kind of science zone that honors both precision and mystery, logic and wonder, numbers and narratives. In that science, the cosmos is not merely a thing to be measured, but a story to be told. And we, as observers and participants, are not merely passive minds, but vital voices in that unfolding epic. The final confrontation is happening now. It is happening in labs and blackboards and satellites, in code and data and debate. It is happening in the questions we teach, the missions we fund, the conversations we have late into the night. And it will not end in a final answer, but in a deeper question, a better model, a clearer vision of what it means to be small in an infinite universe, and to seek the truth anyway. That is the legacy of cosmology. That is the path forward. In the grand narrative of human history, the pursuit of cosmic understanding stands as one of our most profound and defining endeavors. We have always looked upward at, first with wonder, later with instruments, and now with theories and technologies that pierce the very fabric of space and time. Yet even as we decode the signals from the stars, peer into the darkness between galaxies, and model the birth of time itself, a deeper thread runs through this journey on, not written in equations or pixels, but in the quiet stirrings of the human spirit. The moral takeaway of cosmic exploration is not merely the accumulation of facts, but a transformation of perspective. It is about what happens to us, not just what we discover. In exploring the unknown, we learn not only what the universe is made of, but who we are, what we value, and how we choose to live in a world we now understand to be unimaginably vast, ancient, and interconnected. The most fundamental lesson is this: curiosity is not a luxury, it is a necessity. It is not merely a trait of scientists, children, or dreamers. It is the engine of our survival and the hallmark of our progress. Curiosity is what lifted early humans from caves and drove them to map the skies, plant crops, and build cities. It is what turned fire into electricity, wanderlust into rockets, and questions into revolutions of thought. In science, curiosity is the one constant force that pushes the boundaries of knowledge forward, and nowhere is that more evident than in cosmology. The drive to understand what lies beyond the stars has led us to build tools of astonishing precision, to unify fields of study that once stood apart, and to confront ideas that challenge not just our intellect, but our identity. The exploration of the universe is the clearest expression of curiosity in its purest form, not driven by profit, immediate utility, or survival, but by wonder itself. We ask what the universe is not because we must, but because we can. And in doing so, we affirm that the human mind is not limited by its origin or environment, but capable of reaching beyond what is visible, tangible, or known. And yet, as our knowledge grows, so does the mystery. This is the paradox at the heart of scientific discovery. Every answer begets more questions. Every map reveals new edges. The more we understand the universe, the more we are confronted by what we do not, and perhaps cannot, know. We have measured the rate of cosmic expansion, but not the true nature of dark energy. We have confirmed the presence of dark matter, but not its composition. We can simulate the birth of stars and galaxies, but not the singularity that birthed time itself. In this dance between the known and the unknown, we are forced to balance two competing truths: that knowledge is possible, and that mystery is inevitable. This balance is not a failure of science, it is its essence. It teaches us humility. It reminds us that no matter how powerful our models become, they are models still. The map is not the territory. The equations are not the experience. The theory is not the cosmos. From this realization flows a deeper moral insight. To be human is to live with incomplete knowledge and to seek meaning anyway. The universe does not reveal its secrets all at once. It offers them slowly, like a story told in fragments, scattered across light years and eons. Our task is not to demand total understanding, but to listen, to interpret, and to act with wisdom in the face of uncertainty. In this sense, cosmology is not just a scientific field, it is a philosophical and even ethical practice. It asks us to reflect on scale, on time, on interconnection. It reminds us that the atoms in our bodies were forged in stars, that the light we see began its journey billions of years ago, that the laws of physics apply equally across the cosmos. And from this, unity arises, responsibility not just to understand the universe, but to live in accordance with its insights. Perhaps the most transformative insight is this: we are small, but we matter. On the scale of galaxies and epochs, our lives are brief and microscopic. The Earth itself is a pale blue dot, lost in the vastness of a universe that may be infinite. And yet, we are also the only known part of the universe that knows it is a universe. We are matter that became aware. We are the way the cosmos reflects on itself. And that awareness gives our actions weight. What we do here, in this tiny corner of space, matters not because it will echo across the stars, but because it defines who we are. The search for cosmic truth is also a search for human truth. It invites us to transcend tribalism, greed, and short-term thinking. It teaches us to see ourselves not as isolated individuals, but as participants in a shared reality that stretches far beyond borders, ideologies, or lifespans. In this way, cosmic exploration becomes a kind of moral mirror. It reflects back to us our capacity for wonder, cooperation, and resilience. But it also reveals our fears, limitations, and blind spots. It shows us that we can launch robots to Mars, but struggle to care for our own planet. That we can detect gravitational waves from black holes, but struggle to hear the suffering of others. The cosmos does not judge, but it does contextualize. It places our struggles and triumphs in perspective. It shows us that conflict is petty when viewed from the stars, that unity is natural when seen from orbit, that survival depends not on dominance, but on harmony. These are not new moral ideas, but they gain new urgency and clarity when framed against the canvas of the cosmos. The ultimate lesson, then, is not just about the universe, but about how we choose to live within it. To explore the unknown is to become more fully human. It is to embrace vulnerability, courage, and imagination. It is to accept that the answers may never be complete and to find meaning in the asking. It is to build telescopes not just for data, but for dreams. It is to teach our children not just facts, but the joy of discovery. It is to weave science, philosophy, and art into a single narrative of awe. And it is to recognize that while we may never find the edge of the universe, we are always capable of expanding the edge of ourselves. This is what we must carry forward. Not just the models, the theories, or the missions, but the spirit. The curiosity that asks what lies beyond. The humility that accepts what we do not know. The wisdom that seeks to live well with others in the face of cosmic vastness. The creativity that dares to imagine new realities. And the hope that, no matter how dark the void may seem, there is always light born in stars, reflected in minds, and passed on in stories, questions, and love. In the end, the greatest truth revealed by the universe may not be found in the particles or the equations, but in using our response to the mystery, in our journey toward understanding, and in the shared wonder that binds us together on this small, fragile world. For all its silence, the universe has spoken, and the moral takeaway is clear. Keep asking, keep learning, keep reaching, not because we will ever know everything, but because the journey itself makes us worthy of the stars. As we stand at the precipice of everything we know, everything we long to understand, the question inevitably arises. Should the mystery remain open, ended? Is there value, even necessity, in not having all the answers? For centuries, science has marched forward on the promise that nature is intelligible, that with enough effort, experimentation, and insight, the veil will eventually lift, revealing the complete workings of the cosmos. Yet, after generations of discovery from heliocentrism to relativity, from quantum mechanics to cosmic expansion, we now find ourselves more uncertain than ever. We've charted the stars, touched the moon, glimpsed the beginning of time, and still, the universe refuses to yield its final truths. Dark matter and dark energy continue to elude direct detection. The fundamental nature of time and space remains unresolved. Quantum gravity, the unification of the large and the small, remains a vision on the distant horizon. And perhaps, most provocatively, the very structure of reality itself, whether it is singular, infinite, simulated, or emergent, may lie forever beyond the reach of complete understanding. And maybe that's the point. Leaving the mystery open-ended is not a failure. It is an invitation. In science, in philosophy, and in life, it is often the unanswered questions that do the most work. They pull us forward. They spark creativity. They force us to explore new perspectives, invent new tools, and stretch the limits of our imagination. The unknown is not a blank. It is a mirror reflecting back to us the values and assumptions we bring to the table. When we ask what came before the Big Bang, we are also asking how we define before. When we ask whether the universe is finite or infinite, we are exploring the limits of measurement, of language, and of comprehension. These are not just technical problems. They are reflections of our humanitarian need for meaning, for coherence, for narrative. And so perhaps the deepest truth is this: we were never meant to solve the universe like a puzzle. We were meant to engage with it like a story, one that unfolds, expands, and evolves with us as we grow. Still, that story has chapters, and what we've learned so far cannot be overstated. First and foremost, we now understand that the universe is dynamic, expanding, and ancient. Once believed to be eternal and unchanging, we now know that everything from the smallest particle to the largest galaxy has a history, a trajectory, and a future. The Big Bang, now supported by extensive observational data, marks not just the beginning of matter and energy, but of time and space itself. We've learned that the universe is flat or nearly flat, and that its fate is governed not only by matter, but by dark energy, a mysterious force that accelerates cosmic expansion and may one day lead to a cold, lonely, and dark future. We've discovered that ordinary matter, the stuff that makes up stars, planets, and people, is only a small fraction of what exists. Dark matter shapes the structure of galaxies and the cosmic web. Dark energy dictates the destiny of the cosmos. We've also glimpsed the power of gravity, not just as a force, but as a geometric property of space-time. Thanks to Einstein's general relativity, we've confirmed that gravitational waves ripples in the very fabric of the universe carry information across the cosmos. And we've even photographed the shadow of a black hole. We've explored thousands of exoplanets and discovered that planets are common, perhaps even more common, than stars. Some of them lie in the habitable zone, raising the possibility that life may not be a cosmic fluke, but a cosmic principle. We've detected complex molecules in interstellar space. We've sent robotic explorers to every planet in the solar system and landed instruments on comets and moons. We've mapped the sky in every wavelength of light, from radio to gamma ray. And in doing so, we've built a layered, multi-dimensional picture of reality. We've also constructed competing theories to unify the micro and the macro, the quantum and the cosmic. String theory offers a vast landscape of possibilities, including the multiverse. Loop quantum gravity suggests a granular, quantized fabric of space and time. The holographic principle proposes that everything we experience in 3 dimensions might be encoded on a 2-dimensional surface. Quantum cosmology rewrites the idea of beginnings, suggesting that time itself may be emergent or illusory. Some speculate that we live in a simulation. Others believe the universe itself may be conscious. These are not fringe ideas. They are born of serious mathematical and physical investigation, and they reflect a growing awareness that reality may be stranger, subtler, and more profound than we ever imagined. And yet, for all this, the biggest takeaway may be a moral one. We are not separate from the cosmos. We are not observers looking in from the outside. We are participants, made of the same elements forged in stars, animated by the same physical laws, connected across space and time by a shared origin. This knowledge, grounded in empirical science, changes how we see ourselves. It challenges us to care for our planet as a rare oasis in a vast desert. It calls us to value cooperation, empathy, and stewardship. It invites us to see our differences not as divisions, but as variations within a single species, born of a single planet, in orbit around a single star. The infinite possibilities of space do not diminish us, they elevate us. They reveal that there is always more to learn, more to explore, more to dream, that for every boundary we encounter, a new frontier opens, that science is not a closed system, but a living dialogue between the known and the unknown, that we are not defined by what we understand, but by our willingness to ask, to imagine, to reach. So should the mystery remain open-ended? Yes, because an open-ended mystery is a gift. It gives each generation a chance to add their voice to the story, to leave their mark not by solving everything, but by illuminating something. It ensures that wonder never dies, that curiosity never sleeps, and that the pursuit of truth remains alive not in a final theory, but in a million questions whispered to the stars. In the end, we may never find the final answer. We may never reach the true edge of the universe or the bottom of reality. But that doesn't mean the journey is meaningless. It means the journey is the meaning. That to be human is to be in motion toward understanding, toward beauty, toward connection. The cosmos will always hold secrets. It will always stretch beyond our grasp. But in striving to reach it, we become more than what we were. We become a species that listens to the dark, that speaks in light, that builds bridges across billions of years, and still has the courage to wonder what lies beyond. So we leave the mystery open not to escape the truth, but to honor it. Not because the questions cannot be answered, but because they are too rich, too vast, and too beautiful to ever be closed. The stars remain, the darkness beckons, and the universe waits not to be solved, but to be met with eyes wide open and hearts ready to dream.